Welcome everyone to a new talk of the virtual seminar on geometry with symmetries. And today it's my great pleasure to welcome Diego Corro from KIT in Germany. And he'll be speaking on Yamabe problems with symmetries. So thanks, Diego.
Okay. Yeah, I thank the organizers for the invitation. I'm very happy to present here. The work I'm going to present is joint work with Raquel Perales and Juan Carlos Fernandez both at UNAM in Mexico. And even before I start, the first example I want to give you of a singular Riemannian foliation is one which you probably already know, which is this one, is the Hopf vibration of S3 by circles. And the idea is that each circle is locally equidistant. So they are parallel in some sense, or in the distance sense. But as you can see, this local condition can still give you a very complicated picture. Okay, so the motivation for the Yamabe problem is the following one. We want to find canonical metrics on a compact manifold. And here canonical, we need to say exactly what we mean. So if we look at the case of dimension 2, we have uniformization theory, and this is telling us that if we are given a Riemannian metric on a surface, orientable surface, we can find a new Riemannian metric U tilde in the conformal class of G, which will have constant sectional curvature equal to -1, 0, or 1. And this depends completely only on the topology of our surface. So basically on the genus. So when the genus is greater than 1, you have curvature -1. When the genus equals 1, you have curvature 0. And when the genus is 0, you have curvature 1. In higher dimensions, we know something not so simple does not hold. The example is in dimension 3. We have Thurston's 8 geometries. So we have a lot of more geometries, but still we could ask, well, I still want to find as a canonical metric, one that has constant curvature in some sense. And I also can ask that it's in the conformal class of a given Riemannian metric. So this is exactly what Yamabe asked. So he asked if we're given a compact Riemannian manifold, can we find a conformal representative of our Riemannian metric such that it has constant scalar curvature? And here, a conformal representative is just original metric multiplied by some smooth function, positive function. So it still is a Riemannian metric. So rewriting is basically, we're given a compact Riemannian manifold. Does there exist a smooth function such that this new metric has constant scalar curvature? And here now, if we allow C to be a function that we're given, this is known as the Kastan-Warner problem, but they are connected. So this problem has been completely solved. First, Yamabe gave a proof that had some gaps in it that were later completely filled by the work of Trudinger, Aubin, and Schoen. And Kastan-Warner approached a problem where C is a function with conditions on the sign of C. And the nice thing about this problem is that it can be written as a PDE. So as a PDE, you get this is the Laplacian of U times this constant, depending only on the dimension, scalar curvature of U equals your function or constant C, with the extra condition that U is positive. And here, this exponent depends only on the dimension of M, and is the Sobolev critical exponent, 2M divided by M minus 2. So this is a geometric problem, but it also becomes an analysis problem. So that's really nice because we have two ways of trying to approach it, or also like two different viewpoints on it. And the idea is that if you find a solution U to the PDE, then writing G tilde as this metric, you obtain the desired metric you're looking for. Okay. So in this work, I'm going to consider Yamabe type equations. So not exactly the Yamabe equation, but a family of them, which are written as like this. And here I'm setting this exponent to be between the Sobolev critical exponent and bigger than 2. And B and C are smooth functions. So it's more like in the Kasten-Barnett problem. Of course, when you set B equals, here I'm missing the 4m divided by n minus 2 times scalar curvature and P equal to the Sobolev critical exponent, you recover the Yamabe or Kasten-Barnett problem. So this family of equations contains the Yamabe equation. And we want to find general solutions to this equation, not only positive ones. And this is a hard problem because in analysis, because the embedding of the Sobolev space into the LP space is in general not compact in this range. So a way to do it, to like find solutions, is to add geometric and topological restrictions. This was first done by Amann and Humbert, who were the first to ask from the geometric viewpoint for general solutions to this equation, and then by Betoit. And here Amann and Humbert impose restrictions on the Laplacian, on the eigenvalues of this operator, Lg of u equal to minus Gu plus Bu. So they imposed restrictions on the first eigenvalue of this, and Betoit imposed conditions on B and also assumptions on the scalar curvature of your manifold to find solutions. Another approach is to add extra constraints to the problem via compatible symmetries. So this was first observed by Ding in '84 when he was considering the Yamabe problem, and he showed that you could find positive solutions using actions of orthogonal groups on spheres. Then in different works, Clapp-Pacella in 2008, Del Pino, Musso, Packard, Pistoia in 2011 and 2013, and Clapp-Fernandez in 2017, they all consider Lie group actions as a notion of symmetry. But in another direction, Henry in 2019 and Fernandez-Petian in 20, they consider isoparametric functions. And I'm going to give the proper definition of this into later on. So to focus just on two of these examples of symmetries, Clapp-Fernandez, they proved that if you have a Lie closed subgroup of the group of isometries, such that the orbits under the action have positive dimension and the action is not transitive, then you can find infinitely many sign-changing solutions, so general solutions which are H invariant. So with group actions, it's possible to find solutions with the extra constraints. And then Fernandez-Petian in 2017, they considered the round sphere and a function that's an isoparametric function onto an interval. And they showed that the PDE actually becomes an ODE over the interval. So somehow they're pushing the PDE from the sphere into the interval and then becomes an ODE. And the takeaway message is that with two different notions of symmetry, we can find general solutions to the Yamabe-Kasten-Barnett problem under symmetry. And moreover, in this case, you have more control over the set of points in the sphere where your solution vanishes. Because of this. So now I want to introduce the concept of singular Riemannian foliations and convince or give good arguments why they should be considered as a general notion of symmetries. So first of all, what's a singular Riemannian foliation? A singular Riemannian foliation on a compact Riemannian manifold is just a partition, which I denote by F, into submanifolds, LP, called leaves, and each submanifold is connected, injectively immersed, and the two following conditions are satisfied. The first is a smoothness condition. This means that there exists a family of smooth vector fields, X alpha, which spans the tangent space of the leaves at any point. So this is just telling us that as we move along different leaves, the tangent space must change nicely, smoothly. And the second condition is the geometric one, which is known as transnormality, or that F is a transnormal system. So we start with a geodesic, gamma of M, and we assume that it's perpendicular to some leaf. Then it must be perpendicular to all the leaves it meets. And this is equivalent to leaves being locally equidistant. And this point corresponds to the Riemannian point. Okay. So I want to stress that the dimension of the leaves is not constant because we allow these vector fields to vanish. That is, this family can be it consists of singular vector fields. And that's where the term singular is coming from. The first examples I'm going to give you are the non-interesting ones, the trivial ones. So maybe we did not split or manifold at all. We just have one leaf, M. And the other trivial example is that maybe we split it or manifold too finely. So each leaf corresponds to just one point. So this one is the one leaf, the trivial one leaf foliation, and this is the trivial foliation by points. Okay, so now let's see a more interesting example, but a concrete one to fix some of the ideas. So we have a singular Riemannian foliation of the two-sphere by circles of longitude. I'm going to show that is actually a singular Riemannian foliation. So each circle is just a circle of longitude. This would be the equator. Then here around, we would have one of the tropics and so on. And here the North and South Pole. So it's clear that by just considering the speed of each curve, we get a spanning family of vector fields, which gets shorter and shorter and shorter until this vanishes on the North and South Pole. Then if the geodesics on the sphere are the great circles, and we know that if a great circle is perpendicular to a circle of longitude, then it must be a great circle going through the North and South Pole, and thus it will be perpendicular to any other circle of longitude it intersects. As we can see, the condition is vacuous on the North and South Pole because any circle of longitude that we take through here must be going through the other pole and thus intersecting everything orthogonally. So thus we get a singular Riemannian foliation. Okay, and moreover, this foliation is given by a rotation. So if we fix the axis going through the North and South, and then we just rotate, we see that this foliation is given by an action of the circle on the two-sphere. But as I said, I want also to convince you that singular Riemannian foliations are a good notion of symmetry. So I'm going to present big families of examples that are singular Riemannian foliations. Okay, before I need to just give a few definitions. So we say that a singular Riemannian foliation is closed if all the leaves are compact submanifolds without boundary. That means each leaf is a closed submanifold. In this case, the leaves are actually embedded into M. Second, we say that a leaf is regular if it has maximal dimension. The dimension of the leaves is capped by the dimension of M, since they're submanifolds. So there must be one of maximal dimension. And actually, when we look at the union of all the regular leaves or all the leaves of maximal dimension, this is the regular set, and it's an open and dense subset. So actually, there are a lot of leaves with maximal dimension. Then the set of all equivalent classes, denoted by this, is called the leaf space of the foliation. And we equip it with the quotient topology, making the projection sending a point into its equivalent class continuous. And this topology can be written quite easily. So a subset in the leaf space is open if and only if its pre-image under pi in M is open. So that's the definition of the quotient topology. And for example, on the example we saw on the sphere, each circle will now correspond to an equivalent class, so it's just a point, and these points are stacked basically along one of the geodesics, going from the north to south. So at the end, we get that the leaf space is just a closed interval, and actually is the closed interval of longitude pi. So as you can see, when the foliation is closed, the Riemannian metric D M induces a new metric, D star, on the leaf space. And moreover, for such a closed foliation, this space has a very nice geometric structure. It's an Alexander space. This means that it has curvature bounded from below, or colloquially that we can say how thick the triangles in MF are. For those who do not know what the idea of the concept of an Alexander space is. Okay, so now I will present families of examples of singular Riemannian foliations. And from this, I hope you can see that this is a good notion of symmetry. So the first examples are Riemannian submersions. So we have a submersion between two smooth manifolds, M and B, each with a Riemannian metric. And we ask that locally they look like the orthogonal projection, meaning that if I identify this space with the tangent space at some point P in M and set up the Riemannian metric at the tangent space, this is just an Euclidean metric, and we have a nice identification with Rn. And here we do the same with the tangent space under the image of P in B, and here with the Riemannian metric. And asking that locally they look like the orthogonal projection just means that when I look at the derivative of pi at P, this is just the orthogonal projection. So here my foliation is given by taking three images of points. The fibers are nice submanifolds in M because it's a Riemannian submersion, and thus we get the smoothness condition. And then the fact that it looks locally like an orthogonal projection is telling me that the fibers are locally equidistant, they're parallel. And here, of course, M will correspond to the quotient space. The second large family is given by compact connectedly group acting by isometries on a Riemannian manifold. Here my foliation is given by the orbits, so I fix a point and then translate it by all the elements in the group, and that's my leaf at P. the Lie algebra of H will span me the time spaces of the orbits, and with this we can see that the smoothness condition is satisfied, and the fact that H is acting by isometries is guaranteeing us that the orbits are locally equidistant, and thus we get a singular Riemannian foliation. And here our leaf space corresponds to just the orbit space. And the last example is given by isoparametric functions. So we have f from a compact manifold into a closed interval smooth, and we assume that there exist continuous functions a from R to R and b from R to R, such that the norm of the gradient of f is controlled by a, and the Laplacian of f is controlled by b. So by taking again pre-images of values in the interval, we get foliation. This condition is guaranteeing me that the leaves are locally equidistant, that the fibers are locally equidistant. And this condition is guaranteeing me that the fibers are nice embeddeds of manifolds. And with this, you can check that actually the smoothness condition is satisfied. And here, again, our leaf space will correspond just to see the closed interval. So as you can see, we have very different concepts all belonging in the same bag with singular Riemannian foliations. And these are concepts that we are interested in Riemannian geometry. So basically fiber bundles, group actions, and this set of isoparametric functions. And before I forget, the isoparametric functions corresponds to codimension one singular Riemannian foliations. But singular Riemannian foliations are consist not only of the union of these three families, there are more. So basically, Münzner in 80 and 81 proved that a codimension one singular Riemannian foliation on the round sphere, its leaf space must be isometric to 0, pi over k, to the closed interval 0, pi over k, with k being one of taking the value of 1, 2, 3, 4, or 6. And actually here, Elie Cartan had classified the foliations for k equal 1, 2, and 3, and he proved that they were given by group actions. And then in 81, Ferus, Karcher, and Münzner classified the case for k equal 4 and proved that in this family, there are infinitely many singular Riemannian foliations which are not given by a group action nor a Riemannian submersion. But since there are foliations of codimension 1, they are determined by isoparametric functions. For this, they used Clifford algebras, and then Marco Radetzky in 2014 to expanded the ideas they used in 81 to produce, using Clifford algebras, to produce singular Riemannian foliations of arbitrary codimension on the round sphere, which are not given by a group action nor a Riemannian submersion, and since they are arbitrary codimension, not by an isoparametric function. So basically, these examples tells us that there are even more foliations than the examples of submersions, group actions, and isoparametric functions. And yeah, here before I forget, the case of 6 is still open, but it's conjectured that all of these foliations are given by group actions. And there's a nice relationship between the foliations by Ferus, Karcher, and Münzner and Radetzky. Namely, if we consider one of the examples given by Radetzky, one can show that there exists a codimension for one foliation given by Ferus, Karcher, and Münzner, such that any leaf of the foliation is contained in a leaf L tilde of the Ferus-Karcher-Münzner foliation containing it. So there's like a symmetry relation between these two. And I'm going to refer to it at the end of the talk. Okay, so with this, I can state the main theorem. So far, there are no questions. So our result is that we start with M, a compact Riemannian manifold, and F, a closing Riemannian foliation that has all leaves of positive dimension. Then we consider two smooth real-valued functions that are constant along the leaves of the foliation, and moreover, C is positive. Then we add this technical condition. We assume that there exists a constant mu positive, such that for any Sobolev functions, the following inequality is satisfied. Here, we're almost taking the Sobolev norm, but inner product, but here we're multiplying by B, and this integral should be bigger than mu times this term, and this is just the Sobolev inner product of U and W and B. I'm gonna translate why we need this condition in a second, but under these assumptions, we can show that there is an infinite number of sign-changing solutions, so general solution to an equation of this form, a Yamabe type equation, with P bigger than 2 and less or equal than the Sobolev critical exponent, and moreover, these solutions are constant along the leaves. So they are preserving our symmetry. And moreover, we can find one positive solution constant along the leaves with minimal energy. So for this solution, when here we're taking B equal to for M over M minus 2 scalar of G and C constant, then this solution is giving us the conformal class with constant scalar curvature, and moreover is constant along the leaves. So somehow we are solving the Yamabe problem, preserving foliations. Okay, so now the technical condition that we need is also known, can be translated also that this operator is coercive. And this condition is basically implying that when we write this a norm that depends on B like this norm has to be equivalent to the Sobolev norm. And later on, we can conclude things using this norm that we cannot conclude using the Sobolev norm. So that's why we ask for this condition to get this equivalence between the norms. And this is trivially satisfied whenever B is positive. And here, basically, we just take mu to be the minimum between 1 and the minimum of B. Okay. And as a corollary of our theorem, we get a new method to yield solutions to the Yamabe problem on the unit sphere, because in the unit sphere, our function B is constant. So it's foliated and it's positive. So this condition becomes vacuous, or it's automatically satisfied. And this is interesting because of the work I presented of Radetzky and Ferus-Karcher and Münzner. There are foliation on Sn, which are not given by group action as parametric functions nor Riemannian submersions. So all the examples I presented of finding solutions with symmetries do not work for this type of foliations, for the Radetzky foliations, but our method does work. And before anybody says something about the positivity of the leaves, this is not a problem because Marco Radeschi, in his thesis, proved that if you have a singular Riemannian foliation on the sphere, this can be decomposed into two foliations. One is a foliation that by points, a trivial foliation by points. And here we're taking the spherical join with another foliation that's called essential foliation, and this one has leaves of positive dimension. And moreover, this will be a sphere, and this will be also a sphere n minus k minus 1, round spheres. So that's why we don't have to worry about the positivity of the leaves. Okay. So in this way, using these foliations, we get potentially new foliated solutions to the Yamabe problem on Sn, and also at the end, I'm going to explain what I mean with potentially new foliated solutions. So some more definitions before I start with the concept of the proof. The Sobolev space is just the closure of taking all smooth functions under this norm, as we have seen from other courses of analysis. And now I define the Sobolev space of foliated functions, denoted like this, is a closure of taking all smooth functions that are constant along the leaves. That means that for any leaf and any 2 points in the leaf, the function is constant along the leaf, fp equals fq. And then this is forming a linear subspace of this, and then we close it under the Sobolev norm to get a closed linear subspace of the Sobolev space of functions. And the first thing we proved is basically that this space is quite rich. It's an infinite dimensional space. And the idea here is that when we look at the regular leaves, which is an open dense subset, it is open. It looks almost like a fiber bundle over an open and dense subset. So this just means that if I look at in M reg mod F at an equivalence class, and I take a look at the pre-image, it looks for almost any point down here, the picture above is just a trivial fiber bond. It's just a product. And thus, when we take here a bump function, here we can then draw this bump function by just moving along the leaves. And in this way, we get a foliated function in the Sobolev space that has very small compact support. And then by taking enough disjoint balls here, we get as many linearly independent functions on the Sobolev space of foliated functions. And thus we get that this is an infinite dimensional space. Okay, so so far no questions. So let's start with the sketch of the proof. To find solutions using a variational approach, it's useful to consider the energy functional of the PD. So this is just something that's eating functions and giving us a value. And basically what you do is pass every term on the equation to the left, and then integrate and hope you find something. And here we are using the following identity, that the Laplacian of G of U times U d vol G equals the norm of the Laplacian of U over to get this term here. Okay, and then the idea is that basically use a critical point of J if and only if it is a weak solution to the partial differential equation. And then to get smooth solutions, basically you use the fact that this equation is elliptic and you can produce smooth solution from weak solutions. So it's enough to look for weak solutions. Okay, so basically we're looking for critical points of J, but we have the following theorem that's, we call it symmetric criticality because it's somehow generalizing a result by Palais. That's known as Palais' principle of symmetric criticality for group actions, but it only, our proof only works for J. So this is saying that if U is a critical point of J restricted to the foliated functions, then it's a global critical point of J. And what the key lemma to prove this theorem is the following one. So if we are giving a singular Riemannian foliation with closed leaves, and we take a function that's on the orthogonal complement to the foliated ones under the Sobolev inner product, then for any Sobolev foliated function, we have that V and W are L2 orthogonal. Or this means basically that H1JMF perp, it's also L2 orthogonal to H1MF. Okay, so now I'm going to give a proof of this statement using heavily this lemma. So we take any Sobolev function and we decompose it on the tangent part to the foliated functions and then the normal part. And we take U to be a critical point of J restricted to the Sobolev foliated functions. So just recall that J equals this, but I can just rewrite this part as the norm I introduced when talking about coercitivity. And this, I just call it UCP. So it's also some sort of absolute value weighted by C. And then using the fact that these are norms, we can compute the derivative of J prime at U and evaluate it at V, and we get the following identity. So now we evaluate in our U critical value and the V we started with. And since it's linear, it's just this part evaluated on the tangent part to the Sobolev foliated functions and the normal part. But by hypothesis, this term vanishes because U is a critical point of J restricted to the Sobolev foliated functions. So we just have to consider this term. We expand it, and here I'm just simplifying this part into this symbol. And now observe that C, this function and these functions are all foliated and Sobolev. Thus, and B2 is in the normal part. Thus, by the lemma, we get that the integral must be 0. So this whole term is 0. We can just get rid of it, and then we just need to consider this part, which was just this term. We expand it, and again we pull out the same trick. So B is foliated, U is foliated, they're Sobolev, so these products is Sobolev, and B2 is normal to the Sobolev foliated functions. So by the lemma, the integral also must be 0. So we can just get rid of it, and we are left with this term. But now we can, again, use the lemma to add a 0, because u is foliated and v2 is perpendicular, so its integral equals 0. And at the end, we get this term, but this is just the Sobolev inner product of u and v2. But now v2 is normal and u is foliated, so it's also 0. And thus we get that u is also a critical point, a global critical point for J. Okay, so next we prove Rayleigh-Kondrashov's Sobolev embedding type theorem that was also proven by Marcos Alexandrino and Leonardo Cavenaghi, which states that the inclusion map taking Sobolev functions into LP is continuous and compact for P in this range. And before, if you remember from the beginning, I said that in general, the Sobolev embedding of all Sobolev's functions into LP is not compact, but when we restrict to foliated ones, it is. So in this way, somehow we are reducing or search for critical point, like considering the whole space of solutions just to foliated ones. And thus we are reducing our equation using symmetries. So with this theorem, we can prove the following compactness theorem, which states that if we start with a sequence of foliated functions, we evaluate them under J and take a limit, and moreover, the derivative is converging to a critical value weakly on dual space. Then there must exist some foliated functions such that the sequence is converging strongly here. And because of this condition, this is going to be a critical point. So the idea to prove the compactness theorem is first to prove that this space is bounded using these and these conditions. This implies that there must exist some limit, some weak limit of the sequence in the Sobolev space. And then you use the fact that this thing is weakly closed. So this weak limit must also be foliated. And then you use this theorem to check that actually your sequence is converging to you in LP strongly. And then you go back to conclude that actually UN was converging to you strongly in the Sobolev space in H1GM. And then, since we're interested in positive solutions in geometry, because we're interested in conformal classes, then using these ideas, the same procedure, we can produce a positive critical point of J in H1JMF in the foliated Sobolev functions that minimizes J. And the idea here is to take tau to be a minimal value, and then we take a convergent sequence, but not on the whole Sobolev space. We restrict it to something that's homeomorphic to the unit sphere here. And then we carry out this process. And then you still need to check that whatever you got was positive, but it can be checked. Okay, so now from the analysis point of view, you're also interested in general solutions. So that means sign changing solutions. And you want, for this, we use a variational principle that was actually first used by Clapp-Pacella in 2008 for something called the Baricon problem in Rn, which is connected to the Yamabe problem. Then Clapp-Fernandez showed that basically this variational principle also worked for Lie group actions. And we just checked that basically this worked for foliations. So it was more checking, like crossing all the T's and dotting all the I's, checking that all the statements hold well. And this statement basically says that if we are given a linear subspace of the foliated functions with dimension k, and here is where we need that this thing is infinite dimensional to take k arbitrary, and then we take some value that's below the supremum of j, there exists a positive critical point of j, which is the one I said in the previous slide, and then k minus 1 pairs of sign changing critical points of j in the foliated ones, such that j1 is attaining this tau, and the value of j over each of the pairs is less than the supremum of j over w. So with this, all of these theorems, we can, and yes, and before I forget, for the proof of this, here we are using strongly that this thing is plus b times is coercive. But we are also using strongly that the dimension of the leaves is positive. So now to give just a very brief sketch of the proof of the main theorem is basically we use this theorem by variational principle to find critical points of j, but restricted to the space of subole foliated functions. By the principle, by the symmetric criticality, we know that there are also critical points of j, so global critical points, and thus there are weak solutions to this one, but they must, by the ellipticity, we obtain foliated smooth functions that are solutions to this equation, and thus that's how we obtain the result. And here we use that we can take k as large as we want to get arbitrarily many sign changing solutions. Okay. So this the problem of determining if you are actually getting new solutions, it's called symmetry breaking. So I will explain it very briefly. We say that a foliation is contained in F tilde, another foliation. If for any leaf of the foliation there exists another leaf L tilde of F tilde that contains it. So basically this is telling us that locally the foliation, so here we have L, and there must exist a new L tilde containing it, but they might be other leaves nearby containing L tilde. Okay, so
Diego, this will be the case, for instance, if you act with a subgroup in an isometric group action.
Yeah, exactly. So if you have like a subgroup H of H tilde, you would get that the orbit under H, which would be here, H of P, should be contained in H tilde of P. Exactly. And this contention for each leaf implies the following reverse contention. So all the Sobolev foliated functions for F tilde are also foliated for L, and I think this was clear from the picture. Here you have L tilde, and here you have the subfoliation. And if you have a function that's constant along all of these L, of course, is constant along each of the small ones. But now the question is, well, if you find a solution here, is it also going to be a solution from here? Like, how big is this containment when you restrict two solutions? And this is relevant because of the examples of Marco Radetzky and Ferus, Karcher, and Münzner. So I said that foliation by Radetzky is contained by a foliation by Ferus, Karcher, and Münzner. And you're finding solutions on the round sphere to the Yamabe problem. So that's like the geometry here is pretty fixed, and it's just a problem about the symmetries. So are you really getting new solution, or you're just recurring the same ones here? That's the question. And we don't have like a good answer for this. We have basically not a good feeling about in which direction you should go. So that's all I wanted to talk to you about today, and then I thank you for your attention.
Thanks, Diego. And thanks for your talk. Are there any questions or comments for the speaker? I see many hands, but I think people are clapping.
May I have
Yes, go
small
ahead,
question?
Leonardo.
Yeah, thank you. Congratulations, Diego. Indeed, very nice work. Just a small question. To prove that your Sobolev space is well defined and has infinite dimension, you don't need to use any kind of average operator, right? You just rely on some algebra of basic functions. Is this true?
It's even more simple than that. It's just looking at the principal stratum. There you have a fiber bundle, and then you're just using like pullback construction. So you don't need.
I see. So it all relies on the regular case.
Yeah.
I see. Thank you very much.
Yeah, and the fact that it's what you're getting downstairs is still an open subset. So if you take small balls, they're like, and take the preimage above, they're gonna be like nice tubular neighborhoods around leaves, and then you're just putting this function along the, like translating it along the leaf.
Yes, and just to be sure right now, you said that your principle of symmetric criticality just work for this kind of function now, especially, right? This is because probably the way that you proved your lemma, like taking this integral and your producting L2 to be zero, right?
Yeah, exactly. I mean, it's let me go back. It's here. Yeah, so it's that, I mean, this lemma is true for single Riemannian with closed leaves, but then you're using really like the structure of the operator J. That here's like this term, it will be zero, this will be zero, and then you cannot just add a last zero term again to get the Sobolev norm.
I see. And just one last question, because to prove like infinitely many solutions, you use some kind of Lister-Schneerman category or something like this, you know, like a principle of deformation or something like this.
Yeah, basically that's some, you use some like topological genius on the space of functions.
And are you aware of any adapted theory of Lister-Schneerman to the content of foliated spaces?
No, probably it works because you do not require any smoothness, really.
Mm-hmm.
You just need to be able to talk of a Sobolev space that has a nice defined gradient.
Yeah, I see.
So,
Thank you very much.
Hey, I have a question if you
Really?
don't mind, if it's possible. I was just wondering, like, the existence of a function be along, like, sufficiently nice along the sort of leaves of the foliation. How restrictive can that be? It is like this. Does that like strongly depends on kind of foliation you have on a particular?
That's a good question. It's coming back to this problem, because you can always subfoliate. For example, you will always have that the trivial foliation by point is contained in any foliation. So when you consider this, you're just considering like the Yamabe problem, standard Yamabe problem. And then it's like, okay, if all solutions are F invariant, F tilde invariant, then basically you are just find the same solution as with the classical theory of Yamabe and stuff, which would be quite surprising, but.
Okay, so on the one hand, you have like this sort of point foliation in which you get the Yamabe, and on the other hand, if you take the entire manifold as a single foliation, then you get a very much like restrictive kind of like requirement. Okay, yeah, no, cool, yeah, thanks. Yeah.
No, this last inclusion that you were asking about, with this one, we are not getting solutions because you need, I mean, I did not write it in the statement, but you need that the foliation is proper. So you're excluding both trivial foliations.
Okay.
But by the work of, independently by the work of Yamabe, you know how to get solutions for this case. Or theory does not apply, but by Yamabe, you know how to get solutions, and then you know how to get solutions. But in this case, it doesn't work.
Thanks.
So, Diego, just a good question. Your theorem says something about the existence of sign changing solutions, right?
Yeah.
And I thought that for the Yamabe problem, I mean, you always refer to this case as the more difficult case, but isn't it the case that when you have, say, the scalar curvature being positive, that's, I mean, when you aim for a positive scalar curvature, that's the hardest case because it's obstructive? Why is the changing sign more difficult?
It's because you don't have a Sobolev embedding. It's just because of a very basic analysis thing.
Only the analytic, okay.
Yeah, so I mean, basically you are trying to do like the obvious approach of taking where was it? Here. You're trying to find like take the infimum of the energy, that should be like a critical point, and then you try to and you take a sequence going there, and then you try to find a limit, right?
Mm-hmm.
But since this part breaks,
right? Okay.
Perhaps can I add some comment about the Ramiro question? Is because can I just add some comment?
Yeah. Please go ahead. Yes.
One comment is that in the case of singular Riemannian foliation, that includes group actions. If you have, like, for instance, the foliation induced by a non-abelian B group, then its positive scalar curvature is no longer obstructed, for instance, by the Lawson-Yau theorem. So this is one reason you could ask why symmetries allow you to make this
That's right. They have,
harder, easier.
yes, whenever you have, yeah, sorry, I completely forgot. But of course, having these actions already implies something about the A-hat genus, right? Okay.
Yes, exactly. You have the vanishing of the heterogeneous, so it's no
Yes.
longer an obstruction.
Yes. Yeah, I remember that's a beautiful paper, the Lawson-Yau. I mean, it's very, very nice.
Yes.
Okay,
The
no,
question
thanks.
is that Lawson-Yau sometimes, like, it reduces the symmetry, but doing Tigger deformations, you can preserve the symmetry. That's the only trick that you must recall here.
Okay. Yeah, I mean, trigger deformation is when you take a product with some bimetric and then you look at the quotient of the diagonal action, right? Something like that.
yeah, exactly.
Okay. Yeah, no, thanks, Elena. That was useful. All right. So is there no further questions for Diego, I think we can thank him again for a nice talk. Stop recording.